Hello everyone, and welcome to today's presentation. I'm excited to have you here as we explore the fascinating topic of the history of remote sensing. On this first slide, we're setting the stage with the title, History of Remote Sensing. Over the course of this presentation, we'll take a journey through how remote sensing has evolved, from its early beginnings to the advanced technologies we use today. So let's get started and discover the incredible story behind remote sensing. The history of remote sensing actually begins with one of the earliest forms of capturing images, photography. It's fascinating to think that the roots of remote sensing are so closely tied to this invention. When we talk about photography, it's interesting to note that the word itself comes from two Greek words. The first is phos, which means light, and the second is graphein, meaning writing. So essentially, photography is about writing or recording with light. This connection highlights how fundamentally important the concept of capturing light is to the development of remote sensing technologies. Understanding this origin helps us appreciate how far we've come from simply taking pictures to using sophisticated tools to observe and analyze our planet remotely. In 1038 AD, we see an interesting milestone with Alhazen, an Arab mathematician, who made a significant contribution to the understanding of optics. He explained the principle of the camera obscura, a device that uses a small hole to project an image of the sun or a scene onto a surface. This was particularly important for observing solar eclipses safely and accurately. What's fascinating is how his work laid the groundwork for future developments in photography and optical science. It highlights how early thinkers like Alhazen helped us better understand light and vision, key themes in the history of technological progress. His insights show us that curiosity and scientific inquiry have always driven innovation, connecting directly to the overall story of how human understanding of optics has evolved over centuries. Let's talk about the camera obscura, which is a fascinating early device related to the development of photography. The term itself means dark room in Latin, and that's exactly what it is, a darkened space with a small hole or lens on one side. When light passes through this small opening, it projects an inverted image of the outside scene onto the opposite wall inside the room. This concept is crucial because it demonstrates how images can be captured and manipulated using simple optical principles. The camera obscura was used by artists for centuries as a drawing aid, helping them achieve accurate perspective and proportions. It also laid the groundwork for the development of photographic cameras because it showcased how light could be used to record images. Connecting this to our overall theme, the camera obscura highlights the fundamental understanding of optics and light that eventually led to modern photography. It's a perfect example of how curiosity and experimentation with natural phenomena paved the way for technological advancements that changed the way we capture and view the world. Let's take a moment to look at some key milestones in the history of remote sensing. Starting back in 1490, Leonardo da Vinci described in detail the principles behind the camera obscura, which literally means dark room. This device was an early tool that helped artists and scientists understand how light projects images. Then, in 1550, Girolamo Cardano improved on this concept by adding optics to the camera obscura, which allowed for creating higher quality images. This was a significant step forward in capturing clearer visuals. Moving ahead to 1614, Angelo Sala discovered that silver salts darken when exposed to sunlight. This discovery laid the groundwork for photographic processes, enabling us to fix images on surfaces through chemical reactions. These early innovations are fundamental to the development of remote sensing technology, connecting our historical roots to the sophisticated systems we use today. Let's take a look at some key dates in the early history of remote sensing and related technologies. In 1666, Sir Isaac Newton was experimenting with a prism. He discovered that when light passes through a prism, it disperses into a spectrum of colors: red, orange, yellow, green, blue, indigo, and violet. This was a groundbreaking observation because it helped us understand the nature of light and color. Interestingly, Newton also found that, by using a second prism, he could recombine these colors back into white light, demonstrating that white light is composed of these different colors. Fast forward to 1676, Johann Christopher Sturm introduced an important optical principle, the relax lens principle. He mounted a mirror at a 45-degree angle to project an image, which was a crucial step toward developing the modern single-lens reflex camera. This innovation was significant because it improved how images are viewed and captured, laying groundwork for advances in remote sensing and aerial imaging. These milestones highlight how fundamental scientific discoveries about light and optics have shaped the tools we use today in remote sensing. They connect directly to our overall theme of how technological evolution has expanded our ability to observe and analyze the Earth's surface from afar. Let's start by looking at some key moments in the history of remote sensing. In 1777, Carl Wilhelm Scheele made a fascinating discovery. He found that silver chromate, when exposed to sunlight, darkened, but it could be rinsed off with ammonia. This left behind the unexposed silver chromate crystals, creating a fixed image. Essentially, this was an early step towards modern photographic film, which is the foundation of capturing images from a distance. Then, moving forward to 1800, Sir William Herschel made another groundbreaking discovery. He measured the temperatures of light that had been split into a spectrum using a prism, what we now call visible colors. But what's really important here is that he discovered thermal infrared electromagnetic radiation. This was a crucial insight because it opened the door to sensing not just visible light, but also heat signatures, which is vital for many remote sensing applications today. These early discoveries laid the groundwork for the sophisticated remote sensing technologies we rely on now, connecting the dots from basic science to practical tools for observing our planet. Let's start our journey through the important dates in the history of remote sensing with a fascinating milestone from 1827. This is when Niepce took what is considered the first photograph of nature. He captured a view of the French countryside through a window using a camera obscura. What's remarkable is how he used a light-sensitive emulsion made from bitumen of Judea, a type of resinous substance, combined with oil of lavender. It was a very lengthy process, taking about 8 hours in bright sunlight to produce that initial image. This moment is crucial because it marks the beginning of capturing images through a camera, laying the foundation for the development of remote sensing technologies we use today. It's a perfect example of how early experimentation with photography eventually evolved into the sophisticated remote sensing methods we rely on now. Let's take a look at some important dates in the chronological history of remote sensing. On this slide, you'll notice the mention of stereographs, which played a crucial role early on. These stereographs consist of 2 pictures of the same scene, taken slightly offset from each other and mounted side by side. When viewed properly, they create a 3-dimensional effect, giving us a better understanding of the terrain or objects in the images. Moving back to the 1830s, we see the invention of stereoscopes. This invention was fundamental because it allowed people to view these stereographs easily, opening up new possibilities for visualizing the world in 3 dimensions. These developments laid the groundwork for modern remote sensing techniques, showing how innovative tools from the past have shaped the way we observe and analyze our environment today. So, back in 1855, James Clerk Maxwell made a significant contribution by describing the color additive theory. This theory is really fundamental because it explains how we perceive color, and importantly, how different colors are created. It forms the basis for understanding color in many technologies, including those used in remote sensing. Essentially, Maxwell showed that by combining different colors of light, we can produce a wide spectrum of colors that our eyes can perceive. This understanding is crucial because it underpins how sensors and imaging systems detect and reproduce colors in remote sensing applications. Recognizing how colors are formed and perceived helps us interpret the images and data we collect from various sensors more effectively. So, this 1855 discovery is a cornerstone in the history of remote sensing, linking the science of light and color perception to practical imaging technologies we use today. Let's take a look at some important dates in the chronological history of remote sensing. Starting way back in 1858, we see a significant milestone. Gaspar Felix Tornachin, better known as Nadar, took the very first aerial photograph. This was done from a captive balloon at an altitude of about 1,200 feet over Paris. This moment is crucial because it marks the beginning of using aerial platforms to capture images from above, which is foundational to remote sensing. It shows how early pioneers experimented with observing the Earth's surface from the sky, paving the way for modern techniques. This historical point really highlights the innovative spirit behind remote sensing and how it has evolved over time to become such a vital tool in various fields today. Let's take a step back to the 1860s, which marks the beginning of what we now call remote sensing. During this period, aerial observations were primarily conducted using balloons, especially for military purposes. It's fascinating to see how these early efforts laid the groundwork for modern remote sensing. For instance, during the Civil War, balloons were used to observe enemy positions and gather intelligence from above. In 1862, balloons were also employed to map forests, which was quite innovative for that time. However, it's interesting to note that, as far as scholars know, these balloons weren't used to capture aerial photographs back then. The idea of aerial photography would come later, but these initial balloon observations were crucial in demonstrating the potential of aerial vantage points. Overall, these early dates highlight the beginning of our understanding of remote sensing from the air, setting the stage for the technological advances that would follow in the coming decades. Let's take a closer look at some key dates in the early history of remote sensing. Starting back in 1873, Hermann Vogel made a significant discovery. He found that by soaking silver halide emulsions, those are light-sensitive materials, in various dyes, he could extend their sensitivity to longer wavelengths, including near-infrared. This breakthrough was crucial because it paved the way for near-infrared sensitive films, which are now essential in many remote sensing applications. Moving forward to 1887, we see that Germans began experimenting with aerial photographs and photogrammetry. They used these techniques to measure features and areas in forests, which was quite innovative at the time. These early efforts laid the groundwork for modern aerial and satellite imagery analysis. And then, in 1889, Arthur Batta took a remarkable step by capturing the first aerial photograph using a kite in La Bruguière, France. This was one of the earliest instances of aerial photography, demonstrating how alternative methods could be used to observe and analyze the Earth's surface from above. All these milestones highlight how curiosity and experimentation drove the development of remote sensing, connecting to our overall theme of technological evolution in observing our planet. Let's take a look at some important milestones in the history of remote sensing. Starting with 1899, George Eastman revolutionized imaging technology by producing a nitrocellulose-based film that kept the clarity of glass plates, and he introduced the very first Kodak camera. This was a significant step because it made photography more accessible and portable, setting the stage for future imaging innovations. Moving into 1900, we see a breakthrough in physics with Max Planck. He revealed the concept of quanta and developed a mathematical description of the black body, which fundamentally laid the groundwork for quantum mechanics. Both of these developments, though in different fields, are connected to our overall theme. Advances in imaging and understanding the fundamental nature of light and energy have been crucial for the evolution of remote sensing technologies. These milestones highlight how scientific progress often builds on previous discoveries, shaping the tools we use today. Let's take a step back and look at some of the earliest moments in the history of remote sensing. In 1903, the Bavarian Pigeon Corps was using pigeons not just for messaging, but also to take aerial photographs. It's fascinating to see how even back then, innovative methods were being explored to observe and gather information from above. This highlights how the concept of remote sensing has been around for over a century, evolving from simple bird flights to sophisticated satellite systems we use today. These early efforts laid the groundwork for the incredible advancements we'll discuss later in this presentation. Let's start by looking at some of the earliest milestones in the history of remote sensing. In 1906, Albert Mall made a remarkable achievement by using a rocket propelled by compressed air to take an aerial photograph from an altitude of 2,600 feet. What's fascinating is that the camera was ejected during the flight and parachuted back down to Earth, showcasing an early example of aerial imaging technology. That same year, G.R. Lawrence was also experimenting with aerial photography. He was using cameras that were hoisted into the air with the help of balloon kites. These experiments laid important groundwork for capturing images from higher altitudes, which is fundamental to remote sensing. Moving ahead to 1907, we see the Lumiere brothers, Auguste and Louis, who developed a simple yet innovative color photography system. They also established the 35mm film standard, which became a cornerstone for motion picture technology. All these early efforts highlight how pioneers were exploring different methods to capture images from above, setting the stage for the sophisticated remote sensing technologies we rely on today. These innovations are key milestones in understanding the evolution of remote sensing and its applications. Let's take a look at some key dates in the history of remote sensing, starting with 1914. During World War I, there was a significant boost in the use of aerial photography. This was mainly because the war highlighted the strategic importance of aerial views for reconnaissance and mapping. However, after the war ended, the enthusiasm for aerial photography and remote sensing tools declined somewhat as interests shifted and technologies evolved. This period really marks the beginning of recognizing the potential of remote sensing, even though it wasn't yet as developed as it is today. Understanding these early milestones helps us appreciate how far the field has come and the foundations it was built upon. Let's start with 1936, when Albert W. Stevens took a groundbreaking photograph that actually captured the Earth's curvature. This was done from a free balloon at an altitude of about 72,000 feet. It marked a significant milestone in remote sensing, because it showed how high-altitude photography could reveal new perspectives of our planet. Moving ahead to 1938, a German general named Werner von Fritsch made a very prophetic statement. He said, "The nation with the best photo reconnaissance will win the next war." This highlights how crucial aerial photos and reconnaissance were becoming, not just for scientific understanding, but for military strategy as well. It underscored the emerging importance of aerial imagery in national security. Then, by 1940, during World War II, we saw the development of more sophisticated techniques in air photo interpretation. The war accelerated advancements in remote sensing technology, allowing for more detailed and accurate intelligence gathering from the air. These key moments illustrate how early developments in aerial photography laid the groundwork for modern remote sensing, emphasizing its strategic importance and technological evolution over time. Let's take a closer look at some key milestones in the history of remote sensing. In 1946, we saw the first space photographs taken from V-2 rockets. This was a groundbreaking moment because it marked the beginning of capturing images from beyond our atmosphere. These early images laid the foundation for future satellite imaging. Then, in 1954, the U-2 aircraft took its first flight. This high-altitude reconnaissance plane allowed us to gather more detailed imagery from the skies, opening new possibilities for Earth observation. These dates are important because they highlight the technological advancements that have propelled remote sensing forward. They show how we've evolved from simple rocket imagery to sophisticated aircraft, and eventually, satellite systems that today provide critical data for various applications. This progression underscores the significance of innovation in expanding our ability to observe and understand our planet. So let's take a look at some key dates in the history of remote sensing, starting with 1957. That year, Russia launched Sputnik 1, which was a really unexpected event at the time. This launch caught a lot of people off guard and had a huge impact because it essentially kicked off the space age. It also served as a wake-up call for many governments around the world, including ours, to prioritize space exploration. This event was pivotal because it demonstrated the potential of space technology, which eventually led to advancements in remote sensing. It showed that satellites could be used for more than just communication or navigation. They could be powerful tools for observing our planet. Overall, Sputnik 1's launch marked the beginning of a new era, where space exploration and remote sensing started to evolve hand in hand, shaping how we view and understand the Earth today. Let's take a look at some of the key dates in the early history of remote sensing. In 1960, TIROS-1 was launched, marking a significant milestone as the first meteorological satellite. This was a major breakthrough because it allowed us to observe weather patterns from space for the very first time. Also in 1960, the U-2 aircraft was shot down over Sverdlovsk in the USSR, highlighting the tense climate of the Cold War and the importance of aerial and satellite reconnaissance. During the 1960s, the United States began collecting intelligence photography from Earth-orbiting satellites, most notably through the Corona program. This program played a crucial role in advancing our remote sensing capabilities, especially for intelligence and national security purposes. These early efforts laid the groundwork for the sophisticated remote sensing technologies we rely on today, connecting directly to the overall theme of technological progress in observing our planet from space. All right, let's take a closer look at some key dates in the history of remote sensing. Starting in 1964, we see the beginning of the Nimbus weather satellite program with the launch of Nimbus 1. This was a significant milestone because it marked one of the earliest efforts to use satellites for weather observation, paving the way for modern meteorology. Then, moving into the late 1960s, we observed the use of Gemini and Apollo space photography. These missions weren't just about space exploration. They also contributed valuable imagery that helped us understand Earth's surface in new ways. This era really highlights how space technology started to intersect with remote sensing, expanding our ability to monitor and analyze our planet from orbit. Overall, these dates show how remote sensing has evolved from initial satellite launches to more sophisticated space photography, setting the foundation for the advanced systems we rely on today. Let's take a look at some important dates in the chronological history of remote sensing. It all began in 1972 with the launch of ERTS-1, which was the first Earth Resources Technology satellite. Later, it was renamed Landsat-1, marking a significant milestone in Earth observation. Also in 1972, NASA's Skylab, America's first space station, provided photographs that we used to produce our first land use maps, showcasing how space technology could be applied to understanding our planet better. Moving forward to 1975, we saw the launch of Landsat-2, continuing the series of satellites dedicated to Earth observation, along with the launch of GOES, which focuses on weather monitoring. Then, in 1977, Meteosat-1 was launched, becoming the first in a long series of European weather satellites, highlighting international collaboration in remote sensing. In 1978, we had the launch of Landsat-3, further advancing our Earth imaging capabilities. That same year, CSAT was launched, marking a major breakthrough as the first civil synthetic aperture radar satellite. This technology allowed us to see through clouds and darkness, providing invaluable data regardless of weather conditions. Together, these milestones illustrate the rapid growth and diversification of remote sensing technologies, shaping how we observe and understand our planet today. Let's take a look at some of the important dates in the chronological history of remote sensing. Starting back in 1978, we saw the launch of Nimbus 7, which was equipped with the Total Ozone Mapping Sensor, or TOMS, as well as the Coastal Zone Color Scanner, CZCS. This was a significant step forward in monitoring Earth's atmosphere and oceans. That same year, GOES-3 was also launched, enhancing weather observation capabilities from space. Moving into 1981, we had the Space Shuttle Imaging Radar, SIRA, which marked a move towards radar imaging from space, providing new types of data. Also in 1981, Meteosat-2 was launched, expanding our weather observation network. In 1982, Landsat-4 was introduced, continuing the Landsat series and improving our ability to monitor land changes over time. Then in 1984, we saw the launch of SIRB, a radar sensor that built on earlier radar technology. That same year, Landsat 5 was launched, further extending our terrestrial observation capabilities. Finally, in 1986, Spot 1 was launched, offering higher resolution imagery and opening new possibilities for detailed Earth observation. These milestones highlight how each development contributed to the evolution of remote sensing, helping us better understand and manage our planet. Let's take a look at some of the key milestones in the chronological history of remote sensing. Starting in 1986, we saw the launch of Spot 1, which marked a significant step forward in Earth observation capabilities. Then, in 1988, several important satellites came into orbit, including IRS-1A, Meteosat 3, and OFIC-1, each contributing to different aspects of remote sensing, from weather monitoring to reconnaissance. Moving into 1989, Meteosat 4 and OFIC-2 were launched, further expanding our ability to observe the Earth from space. In 1990, Spot 2 was launched, continuing the series and improving image resolution and coverage. The early 90s were quite active. In 1991, the European radar satellite known as ERS was launched, providing radar imaging capabilities, alongside IRS-1B and Meteosat 5, enriching our data sources. Then, in 1992, we saw the launch of JERS-1, a Japanese satellite, and the TOPEX/Poseidon mission, which focused on oceanography and sea level measurements. In 1993, Spot 3 was launched, and although Landsat 6 unfortunately failed to achieve orbit, the mission was significant in the ongoing development of Landsat satellites. That same year, Meteosat 6 was launched, further enhancing weather observation. Finally, in 1994, we had the SIR-CXR experiment flying on the Space Shuttle, which was a groundbreaking demonstration of advanced radar technologies in space. All these milestones highlight how rapidly the field has evolved and how each satellite contributed to the expanding capabilities of remote sensing, aligning with our overall theme of technological progress and increasing Earth observation precision. Let's take a look at some key dates in the chronological history of remote sensing. Starting with 1995, we saw the launch of several important satellites like OrbView-1, ERS-2, RadarSat-1, and IRS-1. That year also marked the failure of the OFIC-3 satellite, which reminds us how challenging space missions can be. In the same year, the KH-12 spy satellite was also launched, highlighting the dual use of remote sensing technology for both scientific and security purposes. Moving into 1996, we saw the launch of IRS-P3, but unfortunately, Spot 3 failed to reach its intended orbit. Then in 1997, there was a series of launches with mixed outcomes. OrbView-2 was launched successfully and carried CYFS, but some satellites like GOES-10, DMSP-5D, and EDOS-1 faced failures shortly after launch, with EDOS-1 failing after just 8 months in operation. Additionally, IRS-1D, Meteosat 7, Lewis, and Earlybird experienced failures within days of their launches, reminding us of the inherent risks involved in space exploration. By 1998, the trend shifted slightly with the successful launches of Spot 4, SPIN-2, and JERS-1. These missions contributed significantly to the advancement of remote sensing capabilities, building on the lessons learned from previous years. Overall, this timeline illustrates both the rapid technological progress and the challenges faced in developing and deploying remote sensing satellites. It's a testament to how perseverance and innovation continue to drive the field forward. All right, let's take a moment to look at some of the key milestones in the chronological history of remote sensing. Starting in 1999, we saw the launch of several important satellites and instruments, including Landsat 7, IKONOS, IRS-P4, QuickSat, CBERS-1, Terra with its MODIS and ASTER sensors, Ceres, MISR, MOPITT, and COMPSAT-1. This year marked a significant leap in both the diversity and capabilities of remote sensing technology. Moving on to 2000, notable launches included SRTM from China, which provided critical topographic data, Tsinghua-1, Eros-A1 from Israel, and Jason-1, a satellite dedicated to ocean surface topography. These missions expanded our ability to monitor Earth's surface and oceans with greater detail and accuracy. Then, in 2001, we saw the launch of QuickBird, which became renowned for its high-resolution imaging capabilities, greatly enhancing our ability to observe detailed features on the ground. Finally, in 2002, the list continued to grow with the launch of Aqua, Spot5, ENVISAT, METSAT, ALSAT-1, and the Meteosat second-generation satellites, along with ADEOSky and OFIC-5. Each of these missions contributed unique data and advanced our overall remote sensing capabilities, supporting a wide range of applications from climate monitoring to disaster management. These milestones reflect a rapid evolution in technology, enabling us to gather more precise, diverse, and timely information about our planet. They demonstrate how each launch builds on the previous ones, pushing the boundaries of what remote sensing can achieve. In 2003, we saw a significant leap in remote sensing technology with the launch of several key satellites. First, there was the launch of IceSat and OrbView 3, which marked important milestones in Earth observation capabilities. IceSat, in particular, was crucial for measuring ice sheet mass and sea level changes, providing vital data for climate studies. That same year, Japan launched ALOS, the Advanced Land Observation Satellite, which enhanced our ability to monitor land use, forestry, and disaster management. Alongside these, several other countries contributed to the growing global remote sensing network. Canada launched RadarSat-2, which brought advanced radar imaging to the table, allowing for all-weather, day and night imaging capabilities. China launched CBERS-2, part of the China-Brazil Earth Resources Satellite Program, which aimed to improve resource management and environmental monitoring. Turkey launched the DMC-Bil-Sat, marking its entry into remote sensing with a focus on environmental and agricultural monitoring. Nigeria launched Nigeria-Sat-1, emphasizing the importance of satellite data for development issues like agriculture and urban planning. And finally, the UK launched the DMC UK satellite, further expanding the global reach of remote sensing efforts. These launches in 2003 really highlight how remote sensing was becoming more diverse, international, and capable of supporting a wide range of applications across the globe. This year was a pivotal point that underscored the increasing importance of satellite technology in understanding our planet. Let's take a look at some important milestones in the history of remote sensing. In 2004, China launched the ROCSat-2 satellite, marking a significant step in their space capabilities. Then, in 2005, we saw the launch of TopSat, a microsatellite that offers a resolution of 2.5 meters. This means it can capture fairly detailed images, and it can even relay imagery back to ground stations within its safe image footprint. That same year, Google made a big move by releasing Keyhole, which you can find at EarthGoogle.com. This platform really revolutionized public access to satellite imagery and geospatial data. It made these advanced technologies much more accessible and understandable for everyday users, helping to raise awareness about how satellite imagery can be applied in various fields. Overall, these developments highlight how rapidly remote sensing technology has evolved and become integrated into our daily lives, shaping how we see and understand our planet. Let's take a closer look at the key satellites and launch vehicles that have shaped India's space journey. Starting with the EDUSAT, which was launched to support educational initiatives. Then, we have the INSAT series, including INSAT 4A and 4B, as well as INSAT 3C, 3E, 3A, and 3B, launched between 1999 and 2003, each serving various communication and broadcasting needs. Moving on, the IMS satellite played a vital role in meteorological and environmental monitoring, launched on 10 January 2007. Cartosat 2 and 2A, launched on 28 April 2008, are high-resolution Earth observation satellites used for urban planning, forestry, and disaster management. We also see the IRS series, starting with IRS-P3 in 1996, IRS-1C and 1D in 1995 and 1997, and later IRS-P4 and P6. These form the backbone of India's remote sensing capabilities, enabling applications across agriculture, forestry, and resource management. Other important satellites include KALPANA-1, launched in September 2002 for weather forecasting, and GSAT-2, launched in May 2003, supporting telecommunications. Let's not forget the historic milestones. The launch of ARYABHATA in 1975, which marked India's entry into space research, and the development of launch vehicles like GSLV and PSLV, which have made India self-reliant in satellite launches. Looking at the timeline, the evolution from the earliest satellite, SLV-3, launched in November 1963, to today's sophisticated missions in 2008, illustrates 4 decades of continuous progress. This journey reflects India's commitment to building a robust, application-driven space program and achieving self-reliance in satellite development and launching capabilities. Let's take a closer look at some of the key milestones in the Indian space program, as highlighted on this slide. We see that India launched a variety of satellites over the years, marking significant technological and strategic achievements. For instance, the Mars Orbiter mission spacecraft was launched on November 5, 2013, using a PSLV C-25 rocket, and it represented India's first mission to Mars, showcasing our capabilities in space exploration. Moving to communication satellites, GSAT-7 was launched on August 30, 2013, aboard an Ariane 5 rocket, and it plays a crucial role in military and strategic communications. Similarly, launched in July 2013, also on an Ariane 5, serves both geostationary communication and meteorological purposes, highlighting our dual-use satellite technology. In the navigation domain, IRNSS-1A was launched on July 1, 2013, using a PSLV C-22, and it forms part of our regional navigation system, which is critical for both civilian and military applications. We also see important Earth observation missions like SARAL, launched in February 2013, and RISAT-1 in April 2012, which enable us to monitor environmental and agricultural changes from space, helping in disaster management and resource planning. Additionally, the timeline includes the launch of smaller experimental satellites like JUGNU and SRM-SAT in October 2011, demonstrating our ongoing efforts to innovate and test new technologies in space. Overall, these milestones reflect India's rapid progress across various satellite domains: science, communication, navigation, and Earth observation, each one contributing to our growing space capabilities and strategic independence in space technology. Let's take a closer look at some of the key milestones in our satellite launch history, starting with GSAT-8, which was launched on May 21, 2011, using an Ariane 5 rocket. This is a geostationary satellite, critical for communication services. Alongside it, we have RISAT-2, launched on April 20, 2011, using PSLV C-16, which is an Earth observation satellite, vital for resource management. On the same day, we also launched YOUTHSAT, a smaller experimental satellite, demonstrating our ongoing efforts in small satellite technology. Moving further back, GSAT-5P was launched on December 25, 2010, again with GSLV F-06, further strengthening our geostationary communication capabilities. On July 12, 2010, we launched 2 satellites, SDUDSAT, an experimental small satellite, and CARTOSAT-2B, an Earth observation satellite, both aboard PSLV C-15. This highlights our dual focus on experimental and operational satellites. In April 2010, we launched GSAT-4 with GSLV-D3, another geostationary satellite, and OceanSat-2 with PSLV C-14, emphasizing our Earth observation efforts. The same month, ANUSAT and RISAT-2, both small and Earth observation satellites respectively, added to our diverse portfolio. In October 2008, the Chandrayaan-1 mission marked our first step into lunar exploration, launched by PSLV-C-11. That same year, we also launched CARTOSAT-2A and IMS-1, both Earth observation satellites, showcasing our capabilities in remote sensing. Earlier, in January 2007, we launched CARTOSAT-2 and SRE-1, the latter being an experimental small satellite. Later that year, in September 2007, INSAT-4CR, a geostationary communication satellite, was launched by GSLV F-04, expanding our communication infrastructure. Finally, in December 2005, launched by an Ariane 5 GS rocket, marked another milestone in our geostationary satellite program. Overall, this table illustrates our steady progress in satellite technology, from experimental small satellites to advanced Earth observation and communication satellites, demonstrating our growing capabilities and ambitions in space. Let's take a closer look at some of the key satellites launched over the years. Starting with HAMSAT, which was launched on May 5, 2005, aboard the PSLV C-6 mission. This satellite was experimental and classified as a small satellite, primarily used for communication experiments. On the same day, we also launched CARTOSAT-1, an Earth observation satellite, also on the PSLV C-6. This highlights how multiple satellites can be launched in a single mission to serve different purposes. Moving back a bit to September 2004, we had EDUSAT, or GSAT-3, launched via GSLV F-01. This satellite was a geostationary satellite, designed mainly for educational communication purposes. Back in October 2003, ResourceSat-1, also known as IRSP-6, was launched on PSLV C-5. Its focus was on Earth observation, helping us monitor resources and land use. Earlier, in April 2003, INSAT-3A was launched using an Ariane 5G rocket. This was a geostationary satellite, part of our communication and broadcasting infrastructure. Just a few months later, in September 2003, was also launched on Ariane 5G, further strengthening our satellite communications network. In May 2003, GSAT-2 was launched via GSLV-D2, again a geostationary satellite, continuing our efforts to expand satellite communication capabilities. Going back to September 2002, KALPANA-1, also called METSAT, was launched on PSLV C-4. This satellite focuses on meteorological observations, crucial for weather forecasting and climate studies. In January 2002, INSAT-3C was launched on an H-10-3 rocket, serving as a geostationary satellite for communications. And in October 2001, the Technology Experiment Satellite, or TES, was launched on PSLV C-3, which was focused on Earth observation and experimental technology development. Earlier, in April 2001, GSAT-1 was launched via GSLV-D1, again a geostationary satellite to support our communication infrastructure. In March 2000, it was launched, further strengthening our satellite-based services. Going further back to May 1999, we had OceanSat, also known as IRSP-4, launched on PSLV C-2. Its primary role was Earth observation, particularly for oceanographic studies. Finally, in April 1999, it was launched on an Ariane 42PH-10-3, serving as a geostationary satellite for telecommunications and broadcasting. Overall, these launches reflect our progressive development in satellite technology, covering a wide range of applications from Earth observation and meteorology to communication and experimental missions. Each satellite and launch marks a significant step in enhancing our capabilities and supporting our nation's growth. Let's take a closer look at some of the key satellite launches from this period. Starting with INSAT-2DT, launched in January 1998 on an Ariane 44LH-10 rocket. This was a geostationary satellite designed to provide communication services. Moving back a bit, IRS-1D was launched in September 1997 using the PSLV-C1 mission, and it served as an Earth observation satellite, which highlights our focus on remote sensing capabilities. In June 1997, it was launched on an Ariane 44LH-10-3, again a geostationary satellite, continuing our push into communication infrastructure. Prior to that, in March 1996, IRS-P3 was launched on PSLV-D3 and added to our fleet of Earth observation satellites, emphasizing our growing expertise in remote sensing. Looking further back, IRS-1C was launched in December 1995 with a Molniya rocket, a different launch vehicle, showing the variety of our launch capabilities, and it too was an Earth observation satellite. Then, in December 1995, joined the fleet on an Ariane 44LH-10-3, continuing the trend of deploying geostationary communication satellites. In October 1994, IRS-P2 was launched via PSLV-D2, further strengthening our remote sensing capabilities. Around that time, in May 1994, we launched the SROSS-C2, part of the Rohini satellite series, on an ASLV mission. This was a significant step into space missions beyond just satellites, exploring space technology. In September 1993, IRS-1E was launched on PSLV-D1, again emphasizing our dedication to Earth observation. July 1993 saw INSAT-2B go up on an Ariane 44LH-10+ rocket, maintaining our focus on communication satellites in geostationary orbit. And in July 1992, INSAT-2A was launched, marking another milestone in our geostationary satellite program. Finally, in May 1992, we launched the SROSS-C, part of the Rohini satellite series, on an ASLV mission, which was another important step in our space missions. Overall, this timeline shows the diversity of our launch vehicles, Ariane, PSLV, Molniya, and ASLV, and how we've progressively built our capabilities in both Earth observation and communication satellites, as well as space missions. Each launch has contributed to our growing expertise and infrastructure, setting the stage for the advanced space programs to come. Let's take a closer look at some of the key satellites launched during this period. Starting with the IRS-1B, launched on August 29, 1991, aboard the Vostok rocket, which was primarily used for Earth observation missions. This satellite played a crucial role in gathering valuable data about our planet's surface. Moving back a bit, the INSAT-1D was launched on June 12, 1990, using the Delta 4925 launch vehicle. It was a geostationary satellite, meaning it stays fixed relative to one point on Earth's surface, ideal for communication and broadcasting services. Before that, the launched on July 21, 1988, with the Ariane 3 rocket, also served as a geostationary satellite, further expanding our satellite communication capabilities. Another significant development was the Rohini satellite series, specifically the stretched versions launched on July 13 and March 24 of 1988 and 1987, respectively. The first was an Earth observation satellite launched by the ASLV, and the second was part of a space mission, showcasing the versatility of our satellite programs. In 1988, the IRS-1A was launched on March 17 from the Vostok rocket, marking an important milestone in our Earth observation efforts. Earlier, the Rohini RS-D2 was launched on April 17, 1983, using the SLV-3 rocket. This satellite contributed to our Earth observation capabilities as well. The INSAT-1A, launched on April 10, 1982, aboard Delta 3910 PAMD, was another geostationary satellite, helping to establish a foundation for our satellite-based communication infrastructure. Going further back, the Bhaskara Roman 2 satellite was launched on November 20, 1981, using the C-1 Intercosmos launch vehicle, primarily focused on Earth observation. Finally, the Ariane Passenger Payload Experiment, or APPLE, launched on June 19, 1981, with the Ariane 1 V3, was a pioneering geostationary satellite that contributed to our understanding and development of satellite communication technologies. Overall, these launches highlight the rapid progress and diversification of our satellite capabilities, from Earth observation to communication, forming the backbone of our space program's growth. Let's take a closer look at some of the key milestones in our early space program. Starting with Rohini RSD-1, launched on May 31, 1981, this satellite was part of the SLV-3 series and was primarily used for Earth observation. It played a crucial role in demonstrating our capabilities in remote sensing from space. Before that, we had Rohini RS-1, launched on July 18, 1980, also on the SLV-3 vehicle. This one was more experimental and smaller in size, helping us test the waters for future satellite development. Then there's the Rohini Technology Payload, or RTP, launched on August 10, 1979. This was another experimental satellite designed to validate new technologies for our space missions, again on the SLV-3 platform. Moving further back, we have Bhaskara-I, launched on June 7, 1979, under the C-1 Intercosmos program, which focused on Earth observation. This was our first step into international collaboration and satellite technology for Earth sciences. And finally, Aryabhata, launched on April 19, 1975, also under the C-1 Intercosmos program. This was our pioneering effort as an experimental satellite, marking India's entry into space exploration. Overall, these satellites show a clear progression, from experimental missions to practical applications like Earth observation, and they highlight our growing expertise and international cooperation in space technology. Let's take a quick look at the evolution of aerial photography. As Jensen highlighted in 2000, the journey begins with some early innovative methods. Back in 1858, balloon photography was one of the first ways people started capturing images from above, giving us a new perspective on the landscape. Then, in 1903, pigeon cameras were introduced, which might sound unusual today, but they were a clever way to get aerial shots before airplanes became common. Moving into the 1890s, kite photography was also used, allowing for relatively simple but effective aerial imaging. The major breakthrough came during the World Wars, when aircraft became widely used for reconnaissance and mapping purposes. These military applications really pushed the development of aerial photography techniques. And of course, in 1947, space exploration opened an entirely new frontier, imaging from outer space, providing us with views of Earth from orbit. All these advances, from balloons and pigeons to aircraft and space, show how aerial photography has continually evolved, becoming an essential tool for mapping, surveillance, and scientific research. This progression highlights the importance of technological innovation in expanding our ability to see and understand the world from above. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a look at some of the key satellite sensors and their spatial resolutions, starting with NOAAVHRR, which has a resolution of about 1,100 meters. This means each pixel covers a fairly large area, so it's great for broad-scale climate monitoring, but less detailed for local features. Next, we have GOES satellites, with around 700 meters resolution, primarily used for weather observation and forecasting. Moving on, MODIS sensors offer resolutions of 250, 500, and 1,000 meters, providing a good balance between spatial detail and spectral information for Earth observation. When we get into higher resolution sensors, Landsat's TM and ETM instruments provide spatial resolutions between 30 and 60 meters. These are excellent for land use, forestry, and environmental monitoring. SPOT satellites improve further, offering 10 to 20 meters resolution, which allows for more detailed mapping and analysis. Then we have IKONOS, with resolutions of 4 meters and even 1 meter. enabling very detailed imagery suitable for urban planning and infrastructure studies. Finally, QuickBird pushes the resolution even further, down to about 0.6 meters, capturing very fine details. All of these sensors are multispectral, meaning they collect data across multiple spectral bands. This diversity is crucial because it allows us to analyze different features on the Earth's surface in a more comprehensive way. So, as we can see, the choice of sensor really depends on the scale and detail required for our specific applications. Each offers unique advantages, from broad climate patterns to detailed urban mapping. Now, let's take a closer look at the AVHRR, which stands for Advanced Very High Resolution Radiometer, a key instrument developed by NASA. This device has played a crucial role in Earth observation, especially in monitoring our planet's atmosphere and surface. The AVHRR is capable of capturing high-resolution images across multiple spectral bands, allowing us to analyze various environmental and climatic phenomena in detail. Its data has been instrumental in tracking changes in vegetation, cloud cover, sea surface temperatures, and more. By providing consistent, long-term observations, the AVHRR has helped us understand climate patterns and environmental shifts over decades. This instrument exemplifies NASA's commitment to advancing our knowledge of Earth through innovative technology. It connects directly to our overall theme of utilizing space-based tools to better understand and protect our planet. Now, let's take a closer look at GOES, which stands for Geostationary Operational Environmental Satellites, specifically focusing on their IR-4 instrument. These satellites are crucial for weather monitoring because they stay fixed over the same spot on the Earth, providing continuous, real-time data. The IR-4, or Infrared Channel 4, is particularly important because it helps us observe cloud temperatures and surface features regardless of whether it's day or night. This capability is key for tracking storms, monitoring weather patterns, and improving our forecast accuracy. Overall, GOES IR-4 plays a vital role in our ability to keep an eye on the atmosphere and respond promptly to severe weather events, tying into our broader theme of advanced satellite technology enhancing weather prediction and safety. Let's take a look at MODIS, which has a spatial resolution of 250 meters. This means that each pixel on the data map covers an area of 250 meters by 250 meters on the ground. It's a fairly detailed resolution that allows us to observe landscape features with good clarity. This level of detail is particularly useful for monitoring changes in land cover, vegetation, and other environmental parameters at a regional scale. When we compare it to coarser resolutions, like those in some other satellite sensors, MODIS 250-meter data strikes a nice balance between coverage and detail. In the context of our overall presentation theme, this resolution helps us identify patterns and trends over large areas, but with enough specificity to be meaningful for environmental analysis. It's an important tool in our remote sensing toolkit, especially for applications like tracking deforestation, urban expansion, or crop health. So, understanding the capabilities of MODIS at this resolution helps us appreciate how satellite data can support decision-making and environmental management at various scales. Now, let's take a closer look at Landsat-TM and its use of false color composite imagery. What we're seeing here is a type of satellite image that combines different spectral bands to highlight specific features on the Earth's surface. In this case, the false color composite helps us visualize things like vegetation, water, and urban areas more clearly than standard visible light images. The key point is that by assigning different wavelengths to the red, green, and blue channels, we can detect phenomena that are otherwise hidden or less obvious. This technique is particularly useful in environmental monitoring, land use planning, and assessing changes over time. Essentially, it enhances our ability to interpret the landscape accurately and connect these observations to broader themes like ecosystem health and resource management. Let's take a closer look at the spot, which is 2.5 meters. This measurement is quite important because it helps us understand the spatial positioning and the scale we're working with. When we talk about a 2.5-meter spot, we're referring to a specific area or distance that can be critical for safety, clearance, or operational purposes. It's essential to grasp how this size impacts the overall design or system we're discussing. By focusing on this measurement, we ensure everything fits properly and functions smoothly within the intended environment. Remember, paying attention to these details helps us optimize performance and maintain safety standards throughout the project. All right, let's take a look at QUICK-BIRD, which has a resolution of about 0.6 meters. What this means is that each pixel on the image represents roughly 0.6 meters on the ground. This level of detail allows us to identify objects as small as a small vehicle or a large tree, making it quite useful for detailed mapping and analysis. QUICK-BIRD's high resolution is particularly valuable when precise, detailed imagery is required, such as urban planning, disaster assessment, or environmental monitoring. It's a great example of how satellite technology can provide us with very detailed imagery from space, helping us make informed decisions based on accurate data. This resolution really bridges the gap between broader satellite imagery and very detailed aerial photos. Let's take a closer look at IKONOS, which has a 4-meter multispectral resolution. This satellite has been a significant player in Earth observation, especially for applications requiring detailed imagery. The 4-meter resolution means it can distinguish objects that are at least 4 meters apart, providing a good balance between coverage area and detail. What's particularly interesting about the multispectral capability is that it captures data across different spectral bands beyond visible light. This allows us to analyze various features on the Earth's surface more effectively, such as vegetation health, water bodies, and urban development. IKONOS has contributed greatly to fields like urban planning, environmental monitoring, and disaster management. Its ability to provide high-quality, multispectral imagery makes it a valuable tool for a wide range of remote sensing applications. By understanding the capabilities of satellites like IKONOS, we can better appreciate how satellite technology supports our efforts in observing and managing our planet. Now, let's take a closer look at IKONOS, which is known for its 1-meter panchromatic resolution. This means it captures images with a level of detail that allows us to distinguish objects as small as 1 meter across. Such high-resolution imagery is incredibly useful for a variety of applications, from urban planning to environmental monitoring. It enables us to see features like buildings, roads, and other infrastructure clearly from space, making it a powerful tool in remote sensing. When we consider the overall theme of satellite imagery and its evolving capabilities, IKONOS represents a significant step forward in providing more detailed and accurate data from above. Let's take a moment to look at this image from NASA in 2005. It highlights a key technology called radar, which stands for radio detection and ranging. Now, radar is an incredibly important tool in many fields, especially in astronomy and planetary science. The core idea behind radar is to send out radio waves, which then bounce off objects, like planets, asteroids, or even spacecraft, and return to a receiver. By analyzing how long it takes for those signals to come back and their strength, we can determine the distance, size, shape, and even surface features of distant objects. This technology allows us to explore areas that are otherwise hard to see with optical telescopes, especially through clouds or darkness. It's a powerful way to gather detailed information about our solar system and beyond. So, in the context of our overall theme, radar exemplifies how innovative detection methods expand our ability to study the universe, giving us a deeper understanding of objects that are millions or even billions of miles away. Let's take a moment to look at this beautiful image of Bainbridge Island in Washington. This stunning view was captured using LiDAR technology, courtesy of the Puget Sound LiDAR Consortium in 2005. LiDAR, which stands for light detection and ranging, is a powerful remote sensing method that uses laser light to map the Earth's surface in incredible detail. What makes LiDAR so valuable is its ability to produce highly accurate, three-dimensional data of terrain and landscape features, even through vegetation or in difficult terrain. Throughout this presentation, we've seen how LiDAR helps us understand topography, assess environmental changes, and support planning efforts. So, in essence, LiDAR is a vital tool in our geospatial toolkit, providing precise, detailed information that helps us make informed decisions and better understand our environment.